Alright, in this video we're going to talk about breadth first search, depth first search, and the data structure known as graphs. So there's going to be quite a bit. We're not going to go like super mega ultra deep into every single little thing about each, but we are going to give an introduction. And then in future videos I will go over some problems that have to deal with breadth first search, depth first search, and graphs, and that way you kind of can get a bigger, better handle on them. All right, so first, before we get into BFS versus DFS, by the way, breadth first search I will refer to as BFS, and depth first search I will refer to as DFS for short from now on. Now, let's talk about graphs. Graphs is a data structure, and it's very similar to trees. Trees are actually a form of graphs. If you know something about trees, then you know something about graphs. So graphs are fairly straightforward. You have vertices or nodes. All right, let's say you have a vertex here. Let's call it A. Here's A. And let's say you have another vertex, let's call it B. All right, and then you have these vertices and they are connected. All right. Now, with graphs, there is the important thing you know is the direction from one vertex to another. So for example, I'm going to draw an arrow like this from A to B. And what this means is that I are at A, I could go to B. It's possible for me to go to B. But it's not possible for me to go from B back to A. All right, so this is about direction. Okay, so in directed graphs, so this is directed, there's a certain direction you can go from one node to another, all right? And the arrows will tell you which way to go. So if you're at A, it is possible for you to go from A to B. And then let's just say, like, I don't know, there's another node over here, that's C, all right, where you can go from C to B. Okay, so a directed graph is a graph where there's a direction, like from how you go from node to node, right? And you have to follow the arrow. If there is no arrow pointing, so for example, there is no arrow pointing from like C to A, so I cannot go from vertex C to vertex A because there is no arrow, there's no path, there's no arrow from C to A. All right, so that is a directed. Now, undirected basically means that the arrow goes both ways. Okay, so the opposite would be undirected. All right, just go put un there. Undirected means you can go back and forth. So from A, I can go to B, and from B, I can go back to A. Okay, it goes both directions. Either which way, I can move forward or move back. So you can think of it like a door in a room. You can, walk through the door and go to the next room, and then the door is still there. If you want to go back to the previous room, you just go back. All right, so it's undirected. All right, now, graphs can have cycles. Essentially, graphs can have what we can think of as, hey, if I start off at A, is there a way for me to come back to A? All right, so let's say I started this node right here, and is there a cycle? Is there like some way I can move through the graph and then end up back where I was? In this case, yeah, you can go from A and go to B, go to B then to C, C then to A, right? So there's a cycle. So essentially, what could happen is I could be stuck in this cycle. I could be traversing my graph and I don't really have an endpoint because like I can always come back to where I started. Okay, so that has a cycle. An acyclical graph is the opposite. So basically what that means is that we have vertices, right? But there may not necessarily be a cycle. So for example, if we go from A to B and B to C, it kind of just stops, right? Like there's no cycle. There's no way. If I start off at A, if I continue and traverse the graph according to the arrows, I'm gonna end up at C. And if I end up at C, there's no way to get back to A, so there's no cycle. All right, so if later on we talk about trees, right? Trees are a kind of graph where they are essentially directed and they have no cycles. Okay, so a tree, like a family tree, so for example, like this, start off at the top and then go down. This is a graph too, right? But you're going to basically start at the top and then you go to the bottom and you can't go back up, and there's no cycles. Okay, once you get somewhere, there's no way to kind of go back to where you were, to where you create an endless loop. All right, so what does this have to do with breadth first search and depth first search? So one of the things we have to kind of remind ourselves with DSAs, with data structures and algorithms, is that there is a whole host of very core fundamental ideas that you have to master before you move on to the more complicated ideas, and BFS and DFS are about that. But hopefully this will talk about graphs being directed or undirected, cyclical or acyclical. It's very important you get this. So if that didn't make sense to you, kind of rewind the video and listen to it one more time until you get it, because it's going to be very important for us to talk about breadth first search and depth first search, as long as we understand that graphs have a direction you can go in from vertex to vertex or node to node. You might hear me use the term node or vertex for these circles. Okay, and either the arrows indicate where we can go. If I don't indicate an arrow, it means it's undirected, meaning you can go back and forth. All right, and then certain graphs may have cycles. You start off at a vertex, and it's possible for you to traverse the graph and end up back at the vertex over and over again, which creates a cycle. Some graphs have cycles, some graphs do not, and that just kind of depends. So graph is the overarching data structure. Trees are a kind of graph, and so you can take data structures and you can break them down into subcategories. All right, now that we got the basics of graphs out the way, let's talk about breadth first search versus depth first search. Hi, my name is Jonathan Hopp, and if you're enjoying this tutorial, I invite you to visit my website, codingyourcareer.com. I've got courses on Java, JavaScript, TypeScript, and all of the famous frameworks like React and Angular, the kind of things you'll need in order to break into the world of tech and get the knowledge that you need. It's even great for people who are already in tech and want to level up their skills. So it's codingyourcareer.com. Let's continue with the tutorial. All right, let's do breadth first search. All right, and breadth first search is basically it is a strategy for how you're going to traverse the graph. Are we going to try to dig in as deep as we can, or are we going to try to go wide? All right, breadth of course means wide. Now you'll may notice I have these two brackets up here, and there is a reason I have them here. All right, so we've got our graph, and I've got the arrows showing how we can go from vertex to vertex. And let's say they wanted to program the computer to traverse or go through every node in the graph. Okay, so I want to be able to visit each node. Let me kind of mark that vocab word over here because you're going to see it in problems. Want to visit, okay, the different nodes. That's why I'm going to refer to that from now on. All it basically means is going from node to node. Okay, once I go to a node, it's visited. I've been there. Okay, I've taken pictures. I got the souvenir. Awesome, we've been there, done that. Okay, we're going to start off at A. Okay, A is just the node I'm going to pick for us to begin at. And we're going to do breadth first search. We're going to use this algorithm to get us to traverse the entire graph, if it is traversable. Now, why do I have these brackets here? Breadth first search usually requires a queue. Okay, so a queue is a data structure, much like waiting in line at the grocery store. Okay, so you're waiting in line, you've got your groceries, you're ready to check out. Okay, how does it work? Okay, you get in line. You in queue, meaning you get in line. Now, when you get in line, you don't get in at the middle. You don't cut in front of other people and go to the front, even though you probably would like to do that. You get in the back. Okay, so if you want to get in line, you get in the back. The cashier will basically, serve the first customer in line, check them out. When they're done, they DQ or get out the line, and then the next person is up. Okay, and that's how that works. So breadth first search uses a queue, and I'm going to actually kind of write things out as we go along to help you visualize that. Eventually, we'll do it in code, but I want you to be able to kind of see the algorithm happen. One of the things I think that helps a lot for me personally is visualizing the algorithm. If I can't visualize it, the code is great and all, but I feel like I'm just memorizing it. I'm not actually grasping what it is that I'm doing. All right, enough talk. Let's actually do it. Okay, we're at A. All right, now breadth first search basically says, okay, look at your neighbors. Okay, so A has two neighbors. From A we can go to B because you can see the arrow, and from A we can go to D. So let's in queue those. Let's put those in the queue. All right. So we're basically going to come let's say this is the back and this is the front. All right. We're going to put B in and then we're going to put D in. So I'm going to put B. I'll just do it like this because it's more convenient. B and then D. All right. So that's in the queue. Now the reason we're keeping a queue is because it kind of tells us hey, after we're done with A, where should we go? What should we do? Okay, because the computer needs to have some memory of that. Okay, so we visited A. A has been visited. Praise be. Okay, I'm going to put this in blue to say we visited it. All right, where to next? Well, looks like we're going to go to B next because B is in the front of the line. Okay, so we're going to go to B. All right, we're at B now. Okay, great. Who are B's neighbors? B's neighbors are C and E. So we're going to in queue C and E. I'm going to put C in. I'm going to put E in. All right, great. We visited B. So we're going to DQ it. It's like they're done. They're all wrung out. They got their groceries. They paid their bill. They're gone. All right. So now where do we go? Well, the top of the line right now. okay, is D, okay, because that's the next person in line. So we're going to go to D. D doesn't have any neighbors, so there's nothing more to do with that, right? There's like you can't go from D to anywhere else. You can go from A to D, but you can't go from D to anywhere else because there's no arrow pointing from there. All right. So when we DQ this, right? There's nothing else to add to the queue because there's no neighbors. I'm going to put C and E up a little bit just for clarity's sake. So now C is at the head of the queue, and then E is right behind it. So now that I tell the computer go to C. Okay, cool, we're at C. C has no neighbors, but we mark C as visited. Okay, we've been there, so we're going to say, okay, cool, C, we're going to DQ you, bye. Then we're going to go to E. It asks, hey, does E have any neighbors? Yes, it does. It has F. F is a neighbor. Oops, let me do that in white. Keep everything nice and color-coded. So let's go to white. Here we go, there's F. All right, and we're going to visit E. Cool, E has been visited. All right, we're going to DQ it. Okay, have a nice day. Go to F. F has no neighbors. Okay, we will visit F, and then we'll DQ it. So there we go. This way, we visited every single node in our graph, okay, that we were able to visit. Okay, but see how we did it, though? We started at A, and we went ask its neighbors, okay? Then we went to the next one to ask its neighbors. So what you can think of is breadth first search is kind of like taking the graph layer by layer, all right? We're not going to dig all the way down. We're not going to take like a path. We're just going to kind of take it level by level, step by step, okay? Level at a time. So again, breadth first, meaning we're looking at B and D, and then from B we look at C and E, right? So every time we're always looking at all of our neighbors. Okay, let's kind of take depth first search next. And when we look at depth first search, you're going to see that it works a bit differently, all right? Depth first search is more about, hey, finding how far down I can go, all right, and then checking those paths that way. So once you see the algorithm in action, I think you'll be able to appreciate the difference. Now let's compare depth first search. Now depth first search, you can kind of think of it like going through a maze, right? When you have a maze, a lot of the time what you do is you follow the maze all the way till you get to a dead end, and you backtrack to where you were, and then you try to go through a different path, and then you try to go as far down as you can, and then if you hit a dead end, you come back. So depth first search is more about digging deeper into the graph and going as far down as you can go, and then kind of backtracking. So that's kind of the way I think of it. Now, there's different ways to do traversals with depth first search. We're going to talk about that in a later video. So there's more to talk about here. But what I want to do is I want to go over like a simple way to kind of like think about it because we're still being introduced to these concepts. Now, the data structure that's going to help me keep track of nodes is going to be a stack. So with breadth first search, typically you use a queue. Okay, queue is the data structure that you would use to help you with breadth first search. With depth first search, we're going to use a stack. Okay, so things go on the stack. So just a little quick review of stacks in case you don't understand what a stack is. A stack you can think like lunch trays, right? You put the trays on top of one another, and then when you go for a tray, you take the topmost tray and you pop it. Okay, popping means the topmost thing comes off the stack. And so we're going to stack things on top of one another. And anytime we want to remove something from the stack, it's always going to be the topmost thing. Okay, so we start off at A, just because I said we're starting off at A. And you'll notice that A is in my stack. Okay, cool. We're going to pop A off the stack. Pop. And it comes, just comes flying out the stack. You kind of like think of it that way. And A has two neighbors, B and D. So I'm going to put B and D on the stack. We'll put D on the stack first. So here's D on the stack, and then next is B. Okay, so B will be at the top of the stack, and we can mark A as having been visited. Like we've been here. All right, we rode the roller coaster, and now we're moving on. Okay, cool. Next, we're at B, right? We're going to pop B is at the top of the stack, so that's what we're going to work with. All right, so we're going to pop B off the stack. Pop. Okay, it goes flying off. All right, and who are its neighbors? C and E. So we're going to put those on the stack. Okay, here goes. Oops, let me put that there. So we're going to do E, and we're going to do C. All right, so they go on the stack next. And cool, we visited B. Awesome, no problem. Okay, now see how we're not kind of doing this like in levels. I did in breadth first search we did A, and then we did B and D, And then from B, we did C and E. We're doing it in levels. See how I'm not really doing it that way, right? D is all the way at the bottom of the stack, so we're not going to come back to D for quite some time. All right, so now we're at C. C is at the top of the stack, so we're going to pop it off. And C doesn't have any neighbors, so all we're going to do is we're just going to mark it off as visited. Like, we've been here, awesome, great, we had a great time. Thing on the top of the stack now is E. All right, so we're going to pop that off. All right, and then does E have any neighbors? Yes, it does. It has F. Okay, awesome, F. And then we're going to go, okay, cool, we visited E, awesome. And then F, does F have any neighbors? Nope, we're going to pop that off, has no neighbors, right? And we visit F, and then we will have just D, and then we'll go that way, we'll go D. And eventually, when the whole stack is clear, okay, pop that off. Then we would have visited every single node. Now notice how we didn't do it in layers. We were like A, and then B, and then C, right? And then we went to E, and then F. So we went as deep as we could, okay? And then we came back and then came to the other ones, all right? That's why a stack is a good way of traversing this with DFS. Okay, so when to use one over the other, you might be thinking. Because usually when I teach this, most people are like, well, okay, that's all well and good. I kind of get the idea. But when would you use one over the other? Completely depends. Some cases, you could use either and it would solve the problem. And then the only difference is in terms of big O or time space complexity. It might be one might be better than the other in a given circumstance. There are certain circumstances where BFS makes sense, and there's other circumstances where DFS makes sense. We'll go over when we do more problems. We'll go over into when you might want to use one over the other. But for right now, I think it will take enough effort to understand how each one works. Now, again, I want to just reiterate, and for those perfectionists in the audience, this was just one way to traverse the graph with DFS. There are different ways to traverse. It's called pre-order, in-order, and post-order traversal, but that is a topic for another day. I want to actually spend an entire video on just that topic. So for right now, as long as you understand that depth first search digs down as deep as it can, and then backtracks and then digs down as deep as it can, versus breadth first search, which looks at all the neighbors at once, like kind of like a level, like layer by layer, okay, and goes through the layers until it gets through everything. As long as you can understand that those are the two main differences, okay, that's good enough for now.